Well, hi, and welcome to this first video in a set of 5 videos where I try to give you some example problems that involve pistons and cylinders. So let's go ahead and get started. Okay, here is a very general sketch of a piston and cylinder. Here's a more specific sketch of a piston and cylinder that to some of you may look familiar. But in any rate, this is the first of 5 videos where I'm going to try to illustrate some example problems that I hope look a lot like your homework problems. So here's the overview of this module. First is going to talk a little bit about why do we assign you homework in the first place and what's your professional progression. Want to give you a quick few-minute crash course in trying to pick out word keys. What are some key words that you should be encountering in your homework problems? And then going to look at 2 example problems in this module, one with SI units and one with English units. So here we go. Talk a little bit about your professional progression. Why are we giving you homework? Some classes will be taking up and grading homework. Other classes, you're given homework, but you're not going to be asked to submit it for a grade or anything like that. But I want to encourage everybody to at least try every single homework problem that's assigned. The reason for that is that you're preparing yourselves to take and perform well on your tests, because I want you to get a good grade in this class, and I want you to be able to perform the thermal analyses that we'll be covering in this whole class. And the next step, of course, is that what you're doing is you're preparing yourselves to practice engineering, to be a practicing engineer where there is no answer to check against, there is no solution to check against, and in most cases, there's no one to guide you on how to get started and the steps you need to take. It's going to be all up to you. So, for example, you think, why am I getting these piston and cylinder problems in this class? I don't have any interest in piston and cylinders, and I don't see a lot of applications of pistons and cylinders. Well, here's maybe one. Conceivably, you might be working for an employer where you're asked to do some design or analysis of a piston and cylinder that might look like this piece of equipment. You just never know. So these type of things can crop up as you get into the engineering world. So there's a classic example of a real world piston and cylinder. Little crash course on key words that I want you to look out for and be very aware of. So the first is keeping up with your text material. I am not the poster child for reading everything in my text as a student. I've gone back and reread when I realize I should have read, but this is an example of where you really need to keep up with your text material to get success in this class. For example, a quasi-equilibrium process. I wasn't familiar with that before I started as a student in thermo, but here really want you to go and look at your textbook to understand what is a quasi-equilibrium process and sort of learn. When you see that key word, quasi-equilibrium process, it means it's a process in which there's no friction present. And at all times during the process, the material within the system that you're defining is in an equilibrium state. In other words, quasi-equilibrium process would be one in which there's sort of slow movement of a closed system, not necessarily a rapid movement. Quasi-equilibrium process. Next thing is the keyword closed system. And so recognize that a closed system has a fixed mass as it undergoes a process. So I'm trying to illustrate the difference between an open system and a closed system in this slide. So for a closed system, classic piston and cylinder, the closed system is described as what's contained within this dashed control surface. And let's call it M1. It has a mass of M1. It might be a gas in there. Okay. And let's say this closed system is heated. It does some work and it expands, the volume expands. And so for this closed system, what would you expect M2 to be? Well, Common Sense 101 says it's exactly equal to M1. And for homework problems, for these piston and cylinder closed system problems, we simply say M equals M1 equals M2. So again, keyword closed system. And compared to an open system, here's a little screenshot of a heat exchanger in which we have a liquid coming into this heat exchanger, going through these hairpin tubes and coming out there. So this is a flowing situation where, do you see, if I drew a control surface around all these hairpin tubes, I'd have flow going in and flow going out. That's an example of an open system, which we'll cover later. Another key word is you're going to see in homework problems, it'll mention 1 atmosphere, 1 ATM. Okay. And so recognize immediately that 1 ATM, 1 atmosphere, is a measure of absolute pressure of a gas contained in a piston cylinder. And so 1 atmosphere is commonly observed at sea level. It's called 1 ATM. And I do want you to be able to go in and find in your book the single page of conversion factors, and I've clipped out the little table of pressures. And so you can see that 1 ATM, 1 atmosphere, is 1.01 bars. Okay. And if you dive down, you're going to see that a bar is 100 kPa. So 1 atmosphere is going to be 101 kPa. In English units, 1 atmosphere is 14.7 pounds force per square inch. Okay, and so again, keyword, when you see 1 ATM, that tells you that a pressure is given. 1 bar is 100 kPa. You're going to be able to fish that out from your textbook. 1 atmosphere is 114.7 pounds per square inch, absolute. And if you're interested in finding that in pounds per square foot, you're going to do the units conversion. You say, look, there's 144 square inches in a square foot. And so 1 atmosphere is whatever the numerical result of this number is, 144 times 14.7. Okay, what's work? So you're going to be asked to find this. You may be given this. Very important in thermodynamics class to understand what the word work means. And what it means is essentially the definition of work. It is work is done by a system on its surroundings. If work is done, it's a matter of moving a force through a distance or lift, basically as if a weight were lifted. And so the definition of work for us is work out, the work done by a system, W sub out. Textbook just calls it W. I'm going to suggest that you adopt a habit like I have for years and years. This W out, the work done by a system, is the integral of F dx, a force, the integral of a force that can be variable moving through a distance. And so work is going to have units foot pounds force, and it'll also have units of Newton meters, along with other units. And you say, well, what about an electric motor? In this class, we consider a turning electric motor, in other words, a shaft turning at a certain speed and torque. That's a matter of doing work as well, because in your mind, you can imagine that this turning motor is lifting a weight, if you could wrap a rope around the turning shaft. And so therefore, the battery, the electric power powering the electric motor, is also considered doing work. Let's say volts times amps, that would be power. Now, I'm not going to derive this relation because we're really interested in just illustrating some example problems here. But question is, how is work related to a quasi-equilibrium process? I'm trying to show that for a closed system process in a piston and cylinder, we start at this pressure and volume, P1, V1. We do something, let's say we heat it up. We add heat to this closed system. That's going to make the gas expand. And so it's going to move this piston upwards. It's going to lift the weight of the piston. It's going to lift a weight. Okay. And so your book does a great job, and I'm sure your instructor will do a great job of deriving from this basic fundamental for a quasi-equilibrium process where at all times this closed system is in equilibrium, at all times in equilibrium, that you can derive that the integral of f dx is exactly equal to the integral of p dv, pressure times d volume, right? Integral of p dv. So again, don't just take my word for it. This is derived in the book. It should be derived in your classroom, but we're going to accept that for a quasi-equilibrium process, closed system, workout is the integral of p dv. Okay, so now we can get to some example problems. Just want to work you through some examples to get you more comfortable with what we expect. What we expect your solution to look like. Okay, we expect your solution to look more than a formula, some numbers plopped down, and a result that's circled. So what I want to do is illustrate what's a solution going to look like here. All right, here's the problem. I'll just read it while you read along. A gas is contained in a vertical cylinder fitted with a piston on the top and closed at the bottom, of course. The initial volume of the gas inside the piston cylinder is 0.25 cubic meters. The piston can move in a frictionless manner inside the cylinder. It's going to be quasi-equilibrium. The piston has a mass of 25 kilograms and a diameter of 18 centimeters. Atmospheric air surrounds the piston and cylinder, and the pressure of the surroundings is 1 atmosphere. On the Earth, the acceleration due to gravity is 9.8 meters per second squared. The gas is heated until the volume triples. Okay, so here's the homework problem. A, determine the initial and final pressure of the gas. B, determine the work done by the gas during the process. This is very representative of a homework problem from the textbook, very representative of a quiz question, and it can also be very representative of a test question. So the first thing we're going to do is look for keywords. Okay. First keyword, piston and cylinder. Cylinder fitted with piston. That's going to be a piston and cylinder. What does that tell you? Closed system. So not described in the problem statement. You as an engineer think closed system. Okay. Next keyword to pick out here, frictionless manner. That's your clue to say that the process is quasi-equilibrium. That's going to enable you to integrate for work. Work is integral PDV. Okay. Let's see if we fish out other keywords. Let's see, acceleration due to gravity, 9.8 meters per second squared. That's given. We're going to use that. Gas is heated until the volume triples. Wow, that's given information. So you can write down that V2 equals 3V1. That's going to be very valuable on your sketch. Okay, initial and final pressure. Now you do a little thinking about this and think ahead towards solving the problem. It says that what you're trying to find is the initial pressure and the final pressure. That kind of tells you that for this piston and cylinder problem, you're going to need to do a force balance. You're going to need to draw a free body diagram and do a force balance in order to determine the pressure. And then finally, the work done. Since this is a closed system, quasi-equilibrium process, you're going to use integral of PDV to determine the work out, W sub out. And I hear my little assistant, Tigger. Tigger, come over here. Get on the camera if you can. He's talking to me. We'll ignore Tigger for a minute. All right. First, let's start with a sketch. This is part of your solution. Now, your sketch doesn't have to look as professional looking as mine in PowerPoint. Okay. We're going to need to draw several sketches as part of your solution, but we're going to start with the equipment setup sketch. I'm going to draw a piston and cylinder. I'm going to draw my control surface dash line. I'm going to show Q in, heat being added, and work being done, W out. Okay. Label it state 1. And then I'm going to draw another little piston and cylinder to show that I've got a bigger volume at P2. Okay, same thing. So that's a pretty good start with a sketch. We need multiple sketches for this one. The next thing we're going to do is we're looking to find the pressure. What's P1? What is P1? We need to draw a free body diagram of the piston to solve this problem. So here's the piston, free body diagram. There's two forces pushing down on that piston. First one is really obvious. The weight of the piston, which is mg, the mass of the piston times g, both given. I put a little check mark there. And another thing that's pushing down on the piston is the atmospheric pressure, 1 atmosphere, times the area of the piston. Downward forces, all known, okay? Pushing up, P of the gas, we don't know what that is. We got to find that, times the area of the piston. And so another thing you're going to be able to observe quickly from this is when you look at what's known pushing down, not only are all these things known, they are constant. So the downward forces are constant. Doesn't that mean that the pressure must be constant for this process? Yeah. So quickly, I would write down in my solution P1 equals P2 for this problem, constant pressure process. Now, we're looking ahead towards finding the work. And when you're asked to find the work for a closed system, that is a key to draw a pressure volume diagram in your solution. All right, so this free body diagram is inspiring you, as well as part B, to draw a PV diagram. And here it is. You've said, oh yeah, it's going to be a horizontal line. Pressure is constant. I need to draw my process, state 1 to state 2. And so I'm showing state 1, and here's V1, volume 1, okay? Constant pressure process. I remember from the problem statement, volume triples. V2 is 3V1, and there's my final state. So I've drawn 2 state dots and an arrow depicting the quasi-equilibrium process. And the nice thing about this PV diagram is now I can visualize with my eyes what's the work done. It's a positive number integrating left to right, and I can visually see the work done is it's the area of a rectangle. This pressure, P, whatever that pressure is, P, don't know what it is yet, times delta V, V2 minus V1. Okay, so that's the setup. If this is a quiz, you're getting pretty good partial credit if this is as far as you get. But we're going to do the numerics as well and get a full credit. All right, so now we're going to start working on the solution. Here's our free body diagram. For quasi-equilibrium, the sum of the forces in the y equals 0. That's from your statics. So let's get the expression. We're going to simply sum up let's see, how did I do this? The upward force minus the downward forces. Okay. And I put a check on all the stuff I know. Let me move my face here. Oh, there we go. I moved my face so we can put check marks on everything we know. We've got one equation and one unknown. So we will solve for P of the gas. P1, which is going to equal P2, is equal to P atmosphere plus M piston G over A. One equation and one unknown. Now we're solving this problem. Let's do a units check on mg over A. Pressure of the atmosphere. It's going to be, let's say, 101 kPa, 101 kilonewtons per square meter. So this block of these variables the units had better turn out to be kPa, because we're looking for the pressure of the gas in kPa. All right, so let's see. M of the piston, kilograms. G, meters per second squared, divided by A, meter squared. That gives us kilogram meters per second squared divided by meter squared. Okay, so let's see. We're going to have to simplify this. So here's a meter. It's going to cancel with a meter. So we're going to get kilogram meters per second squared. That's a Newton per square meter. That's PA, pascals. Newtons per square meter is pascals. So make a mental note. We're going to have to divide newtons per square meter by 1,000 to get units of kPa. So we'll be careful as we work through the numbers here. We can't just blindly apply numbers and think we've got to get our units to cancel out. All right, so now numerical evaluation. So let's see. Here's our governing equation that you derived. You didn't get this formula from the book. You derived this, okay? And so we did the units check. We're going to have to divide this term by 1,000 to get KPA units. So here's the D is 8.18 meters. There, we're going to solve the area of the piston, pi over 4D squared. Not going to insult your intelligence on deriving how to do that. Just keep your units straight to get the area in square meters correct. Okay. Let's see. Mass of the piston, mg. And so here is mg over A is 9628 newtons per square meter. You go. Have to divide by 1,000 to get to kPa, thousands. You see how we do that? Okay, so we're going to reduce this 3 decimal points by dividing by 1,000. 9.63 kPa is mg over A. P atmosphere is 101 kPa. That's given. And so let's see, we're going to add 101 plus 9.63 to get the result. P1 equals P2 equals 110.6 kPa. Okay, now that we've got that pressure, we'll determine the work done. I think we've covered this. We're going to look at the area under the curve with our PV diagram we drew early in our solution. Here's V1 given, 0.25. V2 is sort of given, triples, volume triples, 0.75. Here's some result from part A. 110.6 is kPa, kilonewtons per square meter. And so if you do your units check for P delta V, here's P. Oh, I didn't talk enough here about my integral, did I? P is constant for this integral. So we'll pull P out of the integral to integrate dV, which is just V evaluated from V1 to V2. So it's P times V2 minus V1. You do the integral to observe this result. And you see, look at your units. You've got kPa, kilonewtons per square meter here, times delta V, cubic meters. So let's see, that's going to be kilonewton meters, and a newton meter is a joule, so it's kilojoules. And so there we go. And so numerically, we've got our numbers, 55.31 kilojoules, and I have circled my answer. If I'm doing this to turn in as a homework problem, I circle my answer complete with units. So worked out, typical example problem. Okay, example 2. What we're going to do is simply change. It's going to be the same problem, but I have changed the numbers and the units. Okay, I didn't scale the numbers. I've just changed the numbers, made up different numbers. So here is the exact same problem statement. Initial volume of the gas is now 1.5 cubic meters. Okay, the piston has a mass of 20 pounds mass, LBM, 20 pounds mass. A diameter of 6 inches. The atmospheric pressure is still 1 atmosphere. You just have to get your unit straight. And the acceleration due to gravity is 32.2 feet per second squared on the Earth. Okay. Same question, what's the initial and final pressure? Same question, what's the work done by the gas during this process? So exact same, start with a sketch, exact same free body diagram, and exact same pressure volume diagram. Notice how there's no units. There's no units shown on this start with a sketch business. No units. Okay. All right, so now find P of the gas. Looks very similar. I did a copy and paste screenshot for my free body diagram. I did a copy and paste, derive the expression for P of the gas, but now let's be very careful and look at units. P atmosphere. Okay. P atmosphere. I want to give you some advice that when you're solving for pressures in the English system for throughout this whole class, I want to suggest that you work in pounds force per square foot, not pounds force per square inch. This is my recommendation for you. Is now, if you're asked to give a result in PSI, pounds per square inch, you'll go back and you do a units conversion. But in these detailed calculations, strongly recommend you work with pressures in pounds force per square foot, and then transform into PSI. All right. Let's do a units check for this term mg over A, because my suggestion for P atmosphere is going to be units of pounds force per square foot. mg over A, pounds mass, m, g, feet per second squared, A, feet squared. And so so my units are pounds mass feet per second squared per square foot. Ugh. Okay. I can simplify that a little, but do you see that what we need pounds force per square foot, and we don't have that here. We have pounds mass, LBM. That is a different unit. Very important. LBM is a different unit than LBF, pounds force. We got to get a conversion to convert. If I do the simplification of this glob of units, it is pounds mass feet per second squared. Pounds mass feet per second squared. That is not what we need. Here's the path to get what we need. You've got to be able to locate this one-page set of conversion factors in your textbook, whether you're using paper book or an e-book. You've got to find this one page. If you're doing electronic, somehow bookmark this page or save it as a PDF image. Somehow this one page, somehow save it, make a screenshot, do something so that you can quickly find this one page of conversion factors. I've pulled out what you need. 1 pound force, 1 lbf equals 32.174 lb. That's pounds mass. In your mind, the textbook uses lb. You're going to be, if you work in lbm, so lb and in my world, lbm are the same unit, pounds mass, lb, that's pounds mass, times feet per second squared. There's your conversion factor to convert pound mass foot per second squared into pounds force. So here's visually mg, here's mg. This is the units of the mg term, okay? Here's your conversion factor term. And if you look at canceling the units, then you get pounds force as your correct units. Very important to do this. So many students overlook this or treat it lightly, and they get killed on quizzes and tests. I don't want you to get killed on quizzes and tests. So do recognize important key is 1 lbf does not equal 1 lbm. Those are two different units for this class. Some folks from community colleges, some sharp students came in from community college and said, but we used slugs in community college. That is a unit of mass. That is a unit of mass. But I have to tell you, in this class, we do not use slugs. There are some good reasons why we don't, but we do not use that unit of mass in this class. We use the unit of lbm, pounds mass, for some good reasons in this class that I don't really need to go into right now. Okay, numerical evaluation. So very similar. So let's look at the, so here's P of the gas. We've got P atmosphere plus mg over A. Wow, we've got to do some numerical work to get this numerical result. Diameter, I switched it to feet. 6-inch diameter is 0.5 feet. Then I go to the area, pi over 4d squared. I write down the mass of the piston and g with my units. I calculate mg over A because that's one of my downward forces. And I get this big number, 3279.8 pound mass feet per second squared. That's not pounds force. So I've got to use my conversion and check my units to get pounds per square foot. Mg over A, that should be a capital A, by the way. Sorry about that. 101.9 pounds force per square foot. Okay. Atmospheric pressure given. So I'm going to add, 14.7 PSI given. So I've got to multiply by 144 to get P atmosphere is 2116 pounds force per square foot. Okay. I'm getting all my units consistent now. Mg over capital A, 102 pounds per square foot. P atmospheric, 2116 pounds per square foot. I'll add them together to get 2218 0.7 pounds per square foot. And then typically, as a good engineer, I'm going to divide back by 144 to get back into pounds per square inch absolute. So the answer, P1 equals P2 equals 15.4 PSIA, pounds per square inch absolute pressure. Okay, work done. Again, got to do our units check to see what kind of units are we going to end up with here. P times delta V, area under the curve, work out P delta V. Same approach, okay. P, pounds per square foot. This is why I recommend you going in pounds per square foot instead of per square inch. Pounds per square foot pressure times change in volume, cubic feet. That's going to give you foot pounds force. Foot pounds force is going to be our units for work. So here we go. It's a simple matter of doing the math now to get 6656 foot-pounds force. Probably for my final answer, I gave a few too many significant figures. If I were a student and needed to turn this in, I'd call it 6656 foot-pounds force. 4 for this class, about 4 significant figures is about right. 8 significant figures, way too many. Okay. Don't kid yourself with false accuracy. Okay. So anyway, there we go. That's example problem 2. We've gone through 2 example problems. I apologize for maybe it taking long. I wasn't timing myself. I don't have a good handle on the time. But what kind of things did we learn from these 2 examples and the crash course in keywords? Start with a sketch. Look for word keys in the problem statement. That's going to be up to you. Understand what quasi-equilibrium process means. Keep your units straight. Now, and seeking formulas in the textbook is not going to win the day for you. That's a big, important point here. Spending lots of time seeking a formula that works for your homework problem out of the text, that's not going to win the day for you. So you're going to have to bite the bullet and start from fundamentals and go from there. I hope this helps. I hope this helps you get started. Now, we've got 4 more videos to go with piston cylinders. I'm not going to drag out details quite as much in the next videos, but I hope this has helped you as you start your problem-solving work in thermodynamics. Thanks for watching.